Hello and welcome to YMT215 Logic Circuits. We are still discussing Chapter 4, Combinational Logic. In the previous part of this chapter we covered things related to logic expressions and minimum maximum terms, how to express logic gates, or how to realize logic circuits by gates through expressions and so on. Today we will be discussing Karnaugh Maps, the universal property of NAND, and NOR gates, and also the pulse waveform operations. And we will go through these thoroughly, specifically Karnaugh Map. If you remember, in the previous session I said that we may need to simplify logic expressions in different ways. Either by just using the principles of Boolean algebra, we can simplify it, and we will take it in the tutorial. As I promised, very soon I'll start giving you the tutorial sessions in details. Or what we can do is we can use Karnaugh Map. What is the Karnaugh Map? What's the whole concept? The concept is like this. We have a way for mapping the possibilities of all variables that we have in the truth table, the inputs, and we provide their output on that map, and based on that we have certain rhythm for grouping them for basically for the sake of simplifying them or minimizing the expressions available. Okay, what is the Karnaugh Map? Karnaugh Map is a net. It's exactly like a table with rows and columns. Similar to the truth table, however, what we do here is not exactly the same idea of truth table. Rather, we need to have cells, and these cells are represented by usually ones, or the place or the state of no 1, 0, we don't write it. Either 1 or nothing at all. In other cases we provide, instead of 1, we provide 0. And depending on if you are using sum of product terms or product of sum terms, or minimum terms or max terms, min terms or max terms. Let's go with min terms initially, and then we will see. The number of cells in Karnaugh Map is always equal to 2 to n, where n is the number of variables here. So if you are going to compose Karnaugh Map for 2 inputs, it would be 2 to power 2. That is 4. There will be 4 cells. How about 3? 2 to power 3, that's 8 cells, and so on. Okay? You explained to us theoretically about it. How can we have such a scenario in reality? Let's say we have 2 variables, A and B. In Karnaugh Map, we need to line up one of them the vertical way, or vertical axis. A, let's say A here, is going vertically, and B is going horizontally. Okay? What does it mean? The possibilities of A are listed here. 0, 1. What kind of possibilities do we have for A? There is no other than 0, 1. What kind of possibilities do we have for B? 0, 1. So we cover all the possibilities here. All the possibilities are what? A bar, B bar, this is 0, 0. Then 0, 1, A bar, B, 0, 1. Then let me take the pen. Then 1, 0. Or A, B bar, then 1, 1. We covered all the possibilities, A, B. These are all possibilities for 2 variables, which is very uncommon. Usually we have either 3 variables or 4 variables. 5 is also less common. I will not teach it in this semester, and I will not ask questions about it. It's a bit more complicated, and we'll just take your time. There is no need for it to be presented in our course. If you have any application for it, you can use it, but for us, we don't have to waste our time just mapping 5 variables. 3, 4 is usually acceptable and normal. So for 2, This is extremely simple. A, B, A could be 0 or 1, B could be 0 or 1, then map all of them. All the possibilities, A bar, B bar, A bar, B, A, B bar, or A, B. That's it. Alright, so how can we place ones here? I'll explain about it in a few slides, not now. For 3 variables, now it's totally up to you. For the 3 variables, same like here. Either you place B here or A, it's up to you. So the place of B and A is totally up to you. If you provide B here, it's also fine, but pay attention to what you provide in these cells. Things will matter later on. Well, the positioning of A and B here is totally random. It's up to you. But what comes next here depends on them. All right. The same thing goes to 3 variables. If you want, you can place C to the horizontal side and AB to the vertical side. Now, the possibilities of AB, we have 0, 0, 0, 1, 1, 1, 1, 0. Now, why do not we say 1, 0, then 1, 1, exactly like the way we count? Because Karnaugh Map is built based on gray code, not the normal counting we have. For minimizing what? Minimizing the change in the bit rhythm. Means 0, 0, we have here these 2 bits, then 0, 1, only 1 bit change, 0 change to 1, then 1, 1, only 0 is changed to 1, then 1, 0, then 1 is changed to 0. If we place 1, 0 here, we will have 2 bits change, and that's not applicable to Karnaugh. So you have to understand that it's built based on gray code, minimizing the change of the bits, only 1 bit at a time. That's why we don't say 0, 0, 0, 1, 1, 0. We say 1, 1, then 1, 0. 2 variables, then we have 2 to the power 2, 4 possibilities. These are the 4 possibilities. Do not forget. Always students make a mistake with this one. 1, 1 is before 1, 0, a gray code base. Okay. C will not change. It is like B, 0, 1, that's it. So now the possibilities will be filled up here based on what? A bar, B bar, C bar. How do I know? 0, 0, 0. It's A bar, B bar, C bar. The product of terms. Okay. How about here? 0, 0, 1. It would be A bar for A is 0. B bar for B is 0. And C, not C bar. And so on. You carry on the same thing. Let's just take this one. 1, 1, 1. That is A, B, C. Why? It is in uncomplemented state. 1, 1, 1. A, B, C. Take this one. 1, 0, 1. That is A, B bar, C. A, B bar, C. The same thing goes to 4 variables. 4 variables, we list 2 here and 2 here. It's up to you. If you say A, B, C, D, or if you say A, B up here and then C, D down here, it's totally up to you. But then be careful with those. That's it. Now, if you start from here, A, B, C, D, the way it is, it would be, again, 0, 0, 0, 1, 1, 1, 1, 0. The same goes here. 0, 0, 0, 1, 1, 1. Again, it's like the gray code. It's again the gray code. Then 1, 0. Right. So this is the way we create Karnaugh. Now, how do I use it? Karnaugh, as I explained, this is like, let me explain about the adjacency. This is like exactly the way it is built around the gray code. Now, I have to explain this. Now, this cell with this cell are adjacent. Adjacent means what? They can be folded together. One more thing. This cell with this one are also adjacent. This one with this one are also adjacent. So we take cells either vertically or horizontally as adjacent. They are adjacent cells, but we don't take diagonally. What does it mean? Let's say I have here a cell. These are not adjacents. These are not. You don't take diagonal. Either next to it from this side or next to it here, horizontally, vertically is fine. One more thing. If we have a cell here, then this one and this one are also adjacent. It is like foldable. Imagine you hold this as a square in your hand and you fold it. You fold it means what? You pull this side back here, down here, and you pull this side down here. You fold them. So this cell with this one are also neighbor. And the same goes, like if I have these two here, these two all with these two are also adjacent, which can be folded together. But now what I want you to understand is we can go either, we can wrap around. Wrap around means from top side or from this side here, sides here, top and bottom, or from this side, for example, this one, and this one are also adjacent, okay? Or you can go horizontally or vertically, but you can't go diagonal. Either in this direction or this direction is not possible, okay? That's the idea. All right, now look at this. You can wrap around. This one is adjacent with this is possible. This one is adjacent with this is also possible. They are adjacent in terms of horizontal movement. This one is adjacent with this one, vertical movement. This one is adjacent with this one, but not this. Okay, the same goes to this side. This one is also adjacent with this one. We can wrap it around. Okay, while this one here, this one here, is also adjacent with this because it can be wrapped. Hold it from the middle here, from this center here, and fold it. Fold this side here like this, and fold this side like this. You will get these two on top of each other. It's like wrapping around. All right. Why do we do this? This is a concept for what we are going to use next. Now, let's start with the min term, or the SOP, the sum of product terms. How can we map them in a Karnaugh? What we need to do is like this. We have to place all the terms in SOP, product of terms, summed product of terms. Then, whichever product is available, is present, we need to provide one in the Karnaugh map to wherever it is. So we have A, B, C, D, and we have all possibilities here. So if we have A bar, B bar, C bar, D bar, then we have one here. And you go on to the next. The one that is not available, for example, you don't have A, B, C, D, this one, place nothing in it. You don't have to put 0. Just don't place anything. Those which are present, available, provide 1 in their cells. Others do not provide anything. And that's it. Okay. Now look at this. Now let's say we have this expression for these three variables. A bar, B bar, C bar. A bar, B bar, C. A, B, C bar. A, B bar, C bar. Now, in order for you to understand how to place ones here, you need their numerical or digital equivalence. A bar, B bar, C bar is 0, 0, 0. 0, 0, 0 is here. Again, create your map. 0, 0, 0, 1, 1, 1, 1, 0. Remember this one. 1, 1, 1, 0. Okay, then we have for C, 0, 1. So we have A bar, B bar, C bar. This is A bar, B bar, C bar, this one. 0, 0, 0, 0. Sorry, 0, 0, 0, 3 zeros. Okay. Then A bar, B bar, C, 0, 0, 1. Okay. Then A, B, C bar, A, B, 1, 1, C bar, 0. Then we have 1, 0, 0, 1, 0, 0, or A, B bar, C bar. You have already placed these ones. Do not provide zeros here. Don't. Just leave it empty, blank, the way it is. What should we do next? I'll explain it in a while. Let's just understand mapping first. Let's take another example. Again, three variables. A bar, B bar, C. A bar, B, C bar. A, B, C bar. A, B, C. In order for us to place them, we need to map. Map means what? Create your Karnaugh map. A, B, C, the way it is now. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1 for C. Now start mapping. A bar, B bar, C. A bar, B bar, C. 1, place it here. How do I know it is A bar, B bar, C? 0, 0, then 1. Where is it? 0, 0, 1. Okay? Here we have 0, 1, 0. 0, 1, 0. This one. Then here we have 1, 1, 0. 1, 1, 0. Then we have 1, 1, 1. And here we have 1, 1, 1. That's it. That's all. Alright. Let's go next. If we have 4 variables, what will I do? We need to create Karnaugh map. Karnaugh map for 4. We have AB, let's say the vertical side, and then we have CD for the horizontal side. And then we need to map these variables. Mapping them means placing their digital equivalency here. 0, 0, 1, 1. Okay. 0, 1, 0, 0. 1, 1, 0, 1. 1, 1, 1, 1, 1, 1, 0, 0, 1, sorry, 0, 0, 0, 1, 1, 0, 1, 0. These are all, so you need to look for those in the Karnaugh map. Okay? The Karnaugh map is like this. It is 4 by 4, 16 possibilities or cells. Now you need to place those. The first one is A bar, B bar, C, D, or 0, 0. 1, 1, 0, 0 from here, 1, 1 here, you place 1, then 0, 1, 0, 0, 0, 1, 0, 0, this one, then 1, 1, 0, 1, 1, 1, 0, 1, then 1, 1, 1, 1, 1, 1, 1, 1, and so on. You carry on, just placing them based on their digital value in these here. So we have 0, 0, 0, 1, 1, 1, 1, 0 for AB. The same goes for CD, 0, 0, 0, 1, 1, 1, 1, 0. Combine them, it will be 0, 0, 0, 0, this one. Then 0, 0, 0, 1, this one, and so on. Okay. Now, if we have a non-standard SOP expression, means what? Non-standard, let's say we are composing an expression of 3 variables, A, B, C. However, I find one of the components that is not A, B, C. I find it A, B only. C is missing. How will I solve this issue? I have to get it back to the standard form. In order for me to get it back to the standard form, I need to add that missing C. How will I add it? I add C, how? I add C in the negated form and the normal form. So if I say I have A, B bar, what I'm going to have? I will say A, B bar, C bar, or A, B bar, C. That will take me back to A, B bar, but in the expanded formula. I'm using the mathematical expansion here. Of course, this is logic in terms of the Boolean algebra. It's not pure mathematics. Okay? Or in other words, we go to the digital form where it is now, this is 1, 0, A, B bar, it's 1, 0. You add 0 in one side and then 1 in another side, which actually they cancel each other ultimately. Okay? And that takes you to the full version of the formula. A, B bar, C bar, or A, B bar, C. So you got it back from this one. Sorry. You extended this one to these two, and that would be a standard SOP formula. Let's say we may have only one variable from 3 or 4. It's possible. So we have 2 missings, not only 1. If you have 2 missings in this case, what are you going to do? Place B is here not negated, it's not barred, so it is 1. What are the possibilities here for A and C? We have 0 and 0, and we have 0, 1, we have 1, 0, and we have 1, 1. You need to play with all possibilities. So you have 4 possibilities. B only as a variable for 3 term SOP would be expanded to A bar, B, C bar, A bar, B, C, A, B, C bar, then A, B, C, like this. You can't map B by itself. In this case, you have to expand it to this way, then map it. All right. Now look, this is non-standard form again, A bar or AB bar or AB C bar. How do I know it is non-standard? Now look, we have ABC, of course C bar, but I mean as a variable ABC, that means we have 3 variables. Here we have 1, so B and C are missing. Here we have A and B bar, that means C is missing. Expand them. Again, we said for B we have to have only one variable, we have to have 4 in the expansion. For A bar we have to have 4 in the expansion. Now A bar means 0 for all possibilities. Here it was B, 1 for all possibilities. Here bar, it would be 0 for all possibilities. Then what we have? 0, 0, 0, 1, 1, 0, 1, 1. We covered all possibilities for C and B and C, sorry. For A, B bar, then what we do is 1, 0. What's missing? C. C could be 0 or 1. So we have 1, 0, 0, 1, 0, 1. The last one is 1, 1, 0, and that's it. We have all these combinations we need. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. All these. So just one missing here. And this is usually a special case like we have in Karnaugh Map. So we need to expand this expression or this term to get all possibilities and get it back to the standard. All right. How do we use Karnaugh Map for simplification? We said we can use it for simplification. We need to group the largest number of ones, but based on certain rules. Adjacent ones can be grouped together. Grouped together in how many? Either in 1, 1, 1, or 2, or 4, or 8, or in what we are saying here indirectly is 2 to the power n. So 2 to the power 0, 1, 2 to the power 1, 2, 2 to the power 2, 4, and so on. Okay? If you group, you must group the largest number of 2 to the power n ones. You can group only adjacent ones. Okay? And you can group whatever ones which are adjacent more than once. Twice possible, 3 times possible if they are overlapping. Maybe it's not clear now, I will explain to you graphically. So this is exactly what I explained as a rule. If you couldn't understand of what I say now, just watch and maybe you can refer to it back again if you cannot exactly understand. I hope you can. Look at this. If we have it may be given or maybe given as an expression, we map it, then we try to minimize. Minimize means what? Now look, initially what we are going to look, this one here is adjacent with what? With this one, this one, this one. This is possible, this is possible, this is possible, but they are empty. So it is adjacent to no one. I group it only with itself. 2 to 0. That's only 1. Okay? Now, how about this? This is adjacent to this. There is no. It's adjacent to here. Okay, there is. I can group it. So I have a group of two ones. This is adjacent here. This one is adjacent to this. There is no. This one also adjacent here, but there is no. Adjacent here. There is no. Adjacent here. There is. You can take it again. So this one is overlapped. We take it twice. How can we get the expression? Now look at this. This one group, 0, 0, 0, which is A bar, B bar, C, first expression from this one. Done. How about this? 0, 1, now look at this. We are grouping these two. Look at here. 0, 1, 1, 0, 0, and 1 are cancelling each other. A is gone, finished. What is left? B from this side. How about C? Now look, here, from C side, we are grouping these two. It's like folding this one, exactly folding this side. Okay? Here, C only. B, C. B, C. This one, A bar, B bar, C bar, nothing is excluded. How about this? If we fold here, from this side, like from here to here, this side, for these two. Look at this. A, B, nothing would be excluded from here, because there is nothing AB the way it is, just common for these two, but C is changeable, 0, 1. C is changeable, will be cancelled. 0, 1, they cancel each other, changeable. So what will be remained? Then A, B. Don't worry, we will take more examples, so it will be easier for you to understand. Let's just understand now how we can group. Now let's take another example. In order for us to group, we will look for the greatest or the largest group in terms of 2 to power n. 2 to power n means what? These two are adjacent, yes. These two are adjacent, yes. But how about if I look at this? Look at this. These two and these two. Yes, they compose 4 ones group. And this is possible for us to group them. Then we don't group only 2 at a time. We group 4 directly. 4. Okay, how about these two? I can group this one. They overlap. This is possible. Another group. These two also another group. And that's it. You have already grouped all of them. You can't leave any. You must group all of them. Okay, in order for us to simplify it, we will see how we can do it. This is called wrapped around. Why wrapping around? It's like we twist it, we fold. Imagine it's a piece of paper, we fold it from half. This one is like coincided with this, and they are wrapped around. Okay? Look at another example. Let's say we have the Karnaugh map like this. How can we group them? Now look at this part and this part, they are adjacent. So what we do, we wrap around here, along with this. What is left? We can take this one, 4. So here we took 8, wrapping around. Okay, wrap around adjacency. Then we take 4. We always maximize the group. Maximize the group means what? We take the greatest number of ones while grouping. Then what's left? This one. Only 2. And that's how we do it. If you have ones here, you must take all those like this. You don't take only these two. Okay? Maximize the group of ones. Always maximize the group of ones. How about deducing the SOP as I said here? How will I do that? Now I will explain about it. Now when you group these ones in groups or in maximum groups of ones, what you can do? In order for you to deduce or to create the simplest form, remember, if you have A bar in one group, they cancel each other. B bar, they cancel each other. C bar, they cancel each other. D bar, they cancel each other. Okay? All right. So again, we group only cells with ones, and we try to maximize the group. Maximize means what? If you have 4 variables, you may have, 4 variables, you may have 16 cells. You may have all the 16 cells filled up with 1. So they may be filled in with all ones. In that case, we will have only 1, just 1. The output is 1, or the final value is 1. But if we have 8 group like this, 8 group, we will have only 1 variable. These will be reduced to only 1 variable, and we will see how. If we have 4, it will be reduced to 2 variables. If we have 2, it will be reduced to 3 variables. If we have 1, it will remain all variables. Okay? This is the way I explain about it. Now, if you have a 3 map of 3, you may have 2 to power 3, that means 8 possible cells, and these cells may be filled, all of them, by 1s, and in that case the output is 1. Just 1. There is no other thing. 1, only 1. If you have only one, just one cell, then you will have 3 variables. If you have a group of 2 cells, 2-cell group, then you will have 2 variables. If you have 4-cell group, then you have 1 variable. And the same goes to 4 variable. If you have 4, then you will have 1. If you have 3, you will have 2. If you have 2, you will have 4. If you have 8, you will have 1. If you have all cells, you will have just not 1 variable, the value of 1 as a value. Okay? Let's take an example. Now let's say we have this Karnaugh map, and we want to find the simplest expression of this Boolean representation here. In order for us to simplify it, we need to take the largest group of 1s. Now look at the largest group. I said you may take 2, 4, 8, it depends, or 16. 16 is not available. So do we have 8? Yes. Look at this. 1, 1, 1, 1, 1, 1, 1, 1. They are all neighbors. So group of 8 1s resulting in what? Now look. A bar, A, they cancel each other because we are folding all these group all together. Okay, what's left from here? Just B, Y, A, B. Here we have A bar, A, cancelled. What's left? B. Now look at this. Look at the horizontal side. We have C bar D bar, C bar D, D C D, then C D bar. They cancel each other. All of them. Why? Because here we have C bar, here we have C. Here we have C bar, here we have C. They cancel each other. Here we have D bar, here we have D. They cancel each other. Here we have D, here we have D bar. They cancel each other. So when you're folding with all these possibilities, they cancel each other. What's left? Just B. And a group of 8 variables takes you only 1 variable at once in the expression B. Take the 4, the next one. We can't take 6. 6 is not possible. 2 to power n equals to 6 is not exactly a valid number. We can have 2 to 3, that's 8. 2 to 4, that's, 2 to 2, that's 4. Okay, and in that case, what we are having here is a group of 4 numbers, and 2 to 2, that's 4 exactly. What we are looking for here is reducing this. How can we reduce it? Now look at this. It's composed of these 2 columns. Okay, these 2 columns. Now look, A is A bar common, no problem, but B bar B, they cancel each other. So what's left from this side? A bar. Okay, A bar. All right, let's come and check here. What's common for these 2 here? We have C, D, and we have C, D bar. So here, D bar, D cancel each other. What's left? C. So what's left here? A bar, C. Okay, A bar, C. Then, the last one, these 2, the way we learned grouping will result in 3 variables. Now look, A, they're common. B is changeable. B bar, they cancel each other. How about the vertical side? The vertical side here, this one, is just C bar D. There is no exclusion, any exclusion here. So A, C bar D. A, C bar D. And that's it. If you learn what I say, what I just said, then it's all done. You will not have any problem with Karnaugh. Let's try again with another example. Determine the product of terms from the given Karnaugh map can be referred to by K-map and write the resulting minimum SOP expression. Minimum, that means you cannot minimize less than this. This is the minimum expression. All right, now look at the groups that we have. Now we have one here is not adjacent with any. So we can't group it unless just by itself is a group. We can make a group for itself here, and it will be A bar, B bar, C bar. Then, how about these two? Again, we fold here, A will be cancelled. Why? Because changeable, 0, 1, it's cancelled. What's left? B for these two. And from here we have C, BC. How about these two here? This one and this one. Fold will be AB, no change here. AB doesn't change. This one, common. C is changeable. 0, 1, they cancel each other. So the output will be, initially will be, we have AB from here, this one, BC from this one, and then A bar, B bar, C. That's the final expression. You take all these expressions, do not forget to sum them up. Of course, this is Boolean summation or expression or operation. Take another example so that the idea will be more clear. If we have such a representation mapping, now remember that we map the maximum number of ones. The maximum number of ones here is can be wrapped around. Now we have 1, 1 here, 1, 1, they are adjacent. We can wrap them around, wrap them like this way. Bring these two sides together, okay? If we wrap them, now look, A bar, A, they cancel each other. What's left? B bar. B bar is common, keep it. How about here? C, C bar, C, they cancel each other. So what's left is just B bar, this one, from group of 4 ones. Then we have this group. For this group, now look, A bar, A is common, B is changeable, it will be cancelled. So B bar, now look at this, C bar. I'm sorry, A bar, C bar. B is cancelled, A bar, C bar. A bar here, 0, 0 is common, 0, 1, B is cancelled, then C bar. How about this here? Now look at this. Here we have A common, B is changeable. 1, 0, they cancel each other. What's left? A and complemented. Then how about here? This side is B. Sorry, not B, C. I keep getting confused about this. C, not B. Here we have C. This is B here. So A, C, C and complemented, and that's it. So we have A, C bar, A, C. You can't simplify this any further. This is the most simplified based on Karnaugh map. Another example, there are so many examples actually. This is a good example. Why? So you know that these are 4 adjacent. This is possible. 4 adjacent, in this case, it's easy. All these are cancelled. Why? Because they are combined in 4 common group. One group, all these are opposing each other or negating each other, they will be cancelled. So what will be left? A bar B directly. How about this 4? This 4 here, we have A bar B is cancelled, B bar B is cancelled. Here we have C bar D is cancelled. Okay? So what will be left? A C bar. Okay? The last one here, to group A. Now look, A B bar, there is nothing to group with, but here we have. So A B bar will be the same, but here look, C bar D, C D, okay, C bar D, then C D. C will cancel, C bar will cancel C, and what will be left is D only, A B bar D, this one. All right. Another example, you may have so many examples, but let me just tell you that these 4 would be rounded with those wrapped up. So we will have 8. 8, in this case, all these will be cancelled. This one will be cancelled. All of them will be cancelled. Why? Because we have wrapping. Okay, what will be left here in this case? Look, C bar, D bar, C, D. So this one will be CD bar, this one will be cancelled. C is changeable, cancelled. D is D bar for both, common. Only D bar will be left. And so, the rest, you know it. I don't have to explain over and over again. Okay, let's take another example. Use K-map to minimize the following standard SOP expression. So we are giving you an expression. You need to minimize it using K-map. That's possible, and it's a common question that we ask in exams and quizzes. Well, how do you need to do it? This is not really hard. You need to map all of them, okay, in a Karnaugh map. Now remember, these are 3 variables, so we can have A, B, C. And now look, A, B bar C, which is 1, 0, 1. 1, 0, 1. Here we have 1, 0, 1. Place number 1. How do I know? Again, 0, 0, 0, 1, 1, 1, 1, 0 based on gray code, 0, 1 for C. That's it. So here we come to 1, 0, 1. This is the first term. Take the second term, A bar B C, 0, 1, 1, 0, 1, 1, this one. Okay. Then A bar B bar C, 0, 0, 1, 0, 0, 1. This one. Okay. Then we have A bar B bar C bar. This is the easiest. 0, 0, 0. This one. Then we have A B bar C. 1, 0, 0. 1, 0, 0. 1, 0, 0. This one. Okay. And that's it. These are all possibilities. We mapped all of them. What we need to do now, look, 1, 1, they are adjacent, but they are also adjacent with 1, 1 here because we can wrap around. So we have a group of 4 ones. We can wrap all of them here. Okay. In order for us to minimize, what will happen now? Look, 0, 0, 1, 0, A will be cancelled. Okay. And C will be cancelled. 0, 1 will be also cancelled. What will be left? Only B bar. Take this one, left only these 2. We can group them together, overlapping this one for 2 groups. It's possible. Now look, 0, 0 is common, A bar. So we know that we have A bar now. Okay, B is complemented, 0, 1. So it will be cancelled. What is left? C. 1 means C. A bar C, this one. Okay? And that's it. That's the minimum expression. You can't minimize it more than this any further. You may be given 4 expression or 4 variable expression. This is possible. And you may need to be asked to minimize it. Now look, this is 3. That means we need to add what's missing here, A. For us, here in this case, will be A bar C, A bar B bar C bar D bar, and then A B bar C bar D bar. We need to add A bar and A for the same expression to cover all possibilities. Now let's try to map them. A bar B bar C bar D bar. This is one here. Then we have A B bar C bar D bar, A B bar C bar D bar, this one. Okay. A bar B C bar D bar, A bar, okay, B, this one, A bar B, which is 0, 1, 0, 0, 0, 1, then 0, 0, here, this one. Then we have A B C bar D bar, A B C bar D bar, this one. Then we have A bar B bar C D, A bar B bar 0, 0, CD, 1, 1 here. Then we have A, B bar, C, D, A, B bar, C, D, this one. Then we have A bar, B bar, C, D bar, A bar, B bar, C, D bar, this one. Then we have A bar, B, C, D bar, A bar, B, C, D bar, this one. Then we have A, B, C, D bar, A, B, C, D bar. Then we have A, B bar, C, D bar, A, B bar, C, D bar. Okay? So we mapped all of them. Why I'm explaining to you so that you know how we are mapping them. Okay? Now look, the largest number of group, or the biggest group here we can do, is wrapping around these 4 with these 4. Okay, if we wrap around the 4 from this side, from the 4 from this side, these all will be cancelled. 0, 1, 0, 1, 0, 1, 1, 0, they will be cancelling each other. Okay? But from this side, from CD, now look, C bar, C, they will cancel each other. Only D bar will be left, this one. Okay. Now, what else can we wrap? Now we have one here left and one here left. We don't take these two. No, we take 4. As I explained, we take the maximum group. Now you don't take these two together. You take the 4 of them because it's possible to wrap around. Okay? You take the 4 of them. Now we have here A bar, B bar. Here we have A, B bar. So A would be cancelled. A bar with A would be cancelled. Will be B bar from this side, B bar from this side, and from here C, D bar will be cancelled. B bar, C, and that's it. That's the simplest way of the expression given here. You see, if you try to simplify it by Boolean algebra, will take your time, and maybe you will not reach to this formula. But with Karnaugh Map, you'll easily get to the simplified form with just few steps like this. All right. We may use the truth table directly to map in Karnaugh Map. It's easy, just a matter of practice. You need just to set wherever the 1 given to the output in the Karnaugh Map. So 0, 0, 0, you need to place it here. The first cell. Let's say 1, 0, 0, you know where 1, 0, 0, 1, 0, 0, and so on. Okay, that's also possible. It's possible in Karnaugh Map to have something we call don't care condition. Don't care condition is a condition that cannot be achieved, or we don't care if it is achieved even. It doesn't change the output. Now remember, in binary coded decimal, we said we have invalid codes. We have from 0 to 9, then 10, 11, 12, 13, 14, and 15 are not valid or invalid codes. And these are, in this case, don't care. They represent either 0 or 1, it doesn't matter. If you want to represent them 1, it's easy for you to group them. It would be much easier for you to group a larger number of 1s. For example, this is a binary coded decimal for variables. And in that case, starting from 10, this is 9, this is 10, 9 in decimal of course, 10 in decimal as well, 10, 10 is 10, okay? And in that case, don't care, don't care, don't care, because they are invalid. And in that case, if you want to group them, you can provide x, 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 x for all these possibilities. If you want to include them in your simplification, you will have an easier way to represent, like, you know, A, B, C, D. If you don't include them, you will have a larger term, A bar, B, C, D, A, B, C, A, B bar, C bar. It depends. It depends on the application. So if you are allowed to include them as 1, or don't care, include them along with 1, that's fine. If you want to include them 0, depending on the application, then they are not listed, and that's it. Okay. We have the last, not the last part, this is the second part. in this presentation or session, we have the universal NAND and NOR. Universal means what? From using NAND gate, we can create whatever gate you want. We can create an AND, a NOT, an OR, also a NAND itself, and also a NOR. So we can create all of them using NAND gate or combination of NAND gates, not necessarily one. We start by NOT. If you take the two inputs of a NAND gate to the same variable as the input, so A, if you take the two inputs to it, it will be the output will be A bar directly. A and A is A, negated, not A. That's a NOT gate directly. It's easy as is. Now, if you want to get an AND gate from a NAND gate, you take the NAND gate the way it is with its output, and then you connect the output, both of it, to these two input of the NAND, the next NAND gate, and will be just inverted. It is a NAND gate with a NOT gate. It takes you back to AND. Okay? NAND gate AB, it would be A NAND B. Okay? Then, if you negate it, it will be A and B. For OR gate, you need three gates from NAND. The first one to invert A, the first input. The second one to invert the second input. Then the third one to invert their own ANDing. So you AND both of them here, and then take the inversion, you will get back an OR gate. Okay? How about a NOR gate? A NOR gate, if you apply the same here with a NAND gate after this, it's like a NOT gate. A NAND gate after this one will take you to NOR. Okay? That's it. We could produce all possible gates with NAND. That's why we call it universal. How about NOR? We can do that with NOR. The first one, same like NAND. We can connect the two inputs to one point. A would be not A. A or A is A. Take the inversion, NOR or not A. Okay? That's the NOT gate using NOR. How about OR? Take the two variables, take the NOR output, then negate that output. Okay? That's it. It will take you back to OR gate. How about AND gate using NOR? Similar to OR gate using NAND. You invert the first input, okay? Then you take their NOR and will get you back to AND. How about NAND gate using NOR? You just need to invert this. So another NOR gate will take you back to a NAND gate, and that's it. That's why we call it universal. I don't need to explain any further there, but before I go further, I may ask you to compose any logic circuit using NAND or NOR, so you should be able to do it. The pulse waveform operation. The pulse actually is not much different from truth table. For the pulse, you can use 1 and 0 in the truth table, and that's extremely possible. And what you need to do, you need to pay attention to what kind of gate you are having. If you have an AND gate or an OR gate, an AND gate is only high when all inputs are high. An OR gate is always high unless all the inputs are low or 0. If you have a NAND, it's always low, it's always high unless all the inputs are high. NOR is always low unless all the inputs are low, and so on. So you need to manage based on those. If you feel like you are a bit confused and you don't know how to do it, then you take these stages, okay, these like based on the timing diagram I explained to you, and create a truth table. Truth table means what? This part 0, 0, 0, you can put it in a truth table. Then we have 1, 0, also 0. You can place it A, B, C and their states. Here we have 1, 0 for B, 1 for C, and so on. So if you're giving such a circuit or logic circuit, you need to see based on what. You can decompose it. A or B, B or C. B or C is easy, Y is easy. It is high if any of them or both of them are high. Check B or C, well this is high here, this is high here, this one is high here, high here. So based on any of them or both of them, you get another output, Y. Then we have A NAND Y. It's always high, except when both of them are low. So you need to look when Y is low, when all of them, it's always high unless both of them are high. So you need to look for when Y is high and A is high at the same time, that will be low. And so on, okay? If you don't get it this way, you can use truth table or you can decompose it to its final operation and see how things go. How about this one? This is an XNOR. XNOR is represented by AB or not AB, not B, sorry. AB or not A, not B, okay? If we have a waveform, it's exactly like, based on the truth table, it's 1 if they are same, 0 if they are not. So A and B, what matters here is A and B. If they are different, then it's 0, because this is XNOR, the negation of XOR, okay? If they are same, then it is 1 and so on, that's it, okay? If you don't know how to do it this way, do it from the gate 2, gate 3, and then gate 1, or in all of them. All right, you may get more complicated formula like this. Well, you have to work it out by some means. Means what? Either you play with the Boolean expression and you get the output, and based on it you can use the truth table and see the waveform. Or you can get each and every one, and then based on it you can manipulate the output. That's possible. But if, like here, determine the output waveform X, you need to know what are the inputs A, B, and C, so you can get the expression like this, and based on it you can create the output based on A and B and C. If you are unable to catch it using these waveforms, convert them to a truth table. How? This is the value of A, this is the value of B, value of C, value of D for the first row, second row, third row, fourth row, and so on. Based on that, you can check this expression is what exactly, okay? Sum of product terms. All right, and this an exercise. I will not solve this exercise. I will solve it later on in the tutorial. It's about design of a system. That's why I'm not going to discuss it. We leave it to the tutorial. This is the end of the second session, or the second part of chapter 4, and that's the end of the chapter. Until our tutorial time, have a good time. Goodbye.